Welcome back. We have started our discussion now on eventually to atomic force microscope, but we were sort of having some very elementary discussion on STM, trying to understand the basic working philosophy of an AFM, because many of the concepts are similar. Of course, right from the name itself you can find out that atomic force microscope relies on some forces. It is primarily the interaction forces, again between a tip and a surface, and in contrast an STM relies on the tunneling current. However, there are in fact lot of similarities in the way they work, and in fact the limitations of STM, that it requires tunneling current, led to the development of AFM, because if one would have used an STM, one could have been able to utilize this beautiful technique only for conducting samples, but AFM does not have any such limitation, and that is exactly what has made AFM so very versatile. So, we just discussed the so called constant height mode of STM, and what you have realized, if we do a quick recap, I am deliberately going very slowly again, because this is a completely new topic. What you realize is that you can raster or move a tip in very close proximity of a surface, and assuming the surface has some roughness, but it is not too rough so that the tip goes and crashes onto it. It is also not too deep that the separation distance between the tip and the surface becomes too large and the tunneling current drops to 0. You in fact can let the tip move over all the points over the surface back and forth, and can get an idea at every point how your tunneling current varied with the tip. Tunneling current varied with the location, and you can thus get a map of what was the magnitude of the tunneling current at each of these points. Understanding the fact that the magnitude of the tunneling current is lower as the separation distance between the tip and the surface increases, and it is higher when the tip is closer to the surface, you can translate this into a variation in feature height as a function of each point. And what is that? That is nothing but the 3D actual image in height, or actual height information of the surface at every location. Limitation of this constant height mode, it sounds very simple. Limitation, as we already realized, that it cannot handle a rough surface, because the surface has to be very, very smooth in order to let the tip move along a constant vertical height without touching it. Touching will simply lead to tip crash. The tip will become blunt, there will be a short circuiting, and this high value of current will in fact lead to the blunting of the tip, and what will be the consequence? A blunt tip fails to produce tunneling current. So, how does one handle this technique for a rougher sample? And that leads to the introduction, led to the introduction of what is known as the constant current mode. Here there is an additional piece of hardware, and that is a feedback loop. The idea is that you start your scan again at a particular point, where let us say the separation distance is d1, that is a comfortable separation distance. You have, what is a comfortable separation distance? It is a distance at which the tip is not touching the surface, as well as there is tunneling current, right. So, you do not want to be too close, because the tip might crash. You do not want to be too further away, because in that case the tunneling current might drop to 0. So, you are at a comfortable separation distance, you know based on your experience that okay, d1 is such a separation distance which will give a tunneling current of I1 or IT1, which is fine. And from now this point 1, you move your tip just like before to point 2, where the separation distance is different, d2, and since the separation distance according to the drawing d2 is less than d1, therefore tunneling current at that point I2 is higher than I1. But what is the mode you are using? Constant current mode. So, that is, you want to maintain the current to be constant. So, all you do, you generate this error I2 minus I1, do not go for a modulus, because whether it is a positive error or negative error is actually going to give you whether the second point is closer or at a further distance. So, this error is simply fed to the feedback loop here. So, what does the feedback loop do? The feedback loop now has some arrangement. What arrangement I will talk later. In the context of AFM I will explain it better. So, it retracts the tip upward. Okay. Up to what extent? Up to the extent the separation distance at this point again increases and goes back to d1, because in that case the magnitude of the tunneling current again goes back to I1. So, you sort of have a set point, let us say it is on the tunneling current I1, which corresponds to a separation distance d1. You really do not, it is not possible for you to measure the separation distance, but you can measure the tunneling current. So, typically the set point is set on I1, and now you again do the same rastering, right. At every point, now what do you measure? Because now, unlike in the previous case where the tunneling current was different at every point, now that is not the case, because due to the presence of your feedback loop, the tunneling current is in fact same at every location, right. So, however, what you measure is at every location how much your tip has gone up or down. If you just measure this, then what you can do, or you simply measure the location, is a sort of a thought concept I am giving. You simply measure the location of, I mean, let us put it simply, how much the tip has gone up and down. If you can track that, let us say with respect to this point, if we term this to be z equal to 0, you can always identify that, well, here z is equal to plus 2.3 nanometer, next point when it goes here it is minus 1.7 nanometer and something like that, and then essentially at the end you get a data set which is simply x, y and z. It is like a you sort of this rastering over a zone of interest. So, it is a 2D area, let us say from here to here is x, it is y. So, the tip simply moves along the routine of a nested do loop and it gathers the data. So, once you have this data, all you need to do is you simply normalize this data with respect to the minimum and maximum elevations, and you just put it on a grayscale, you get an image that reflects the idea about the topography of the surface. So, again this is something that I will pick up in a bit detail later. So, this is how it works. One thing should be clear to you now, in order to generate a 3D reconstructed image of the true surface, you need some sort of a variation, and in the constant height mode the variation was directly in the magnitude of the tunneling current. Here you do not rely on the magnitude of the tunneling current, because you need to feed an error, and the error from one point to the other, because you have a feedback loop, the error from one point to the other is again the variation of the tunneling current as the tip moves from point 1 to point 2. Point 2 initially the tunneling current, the magnitude of the tunneling current is I2, but once the feedback loop gets activated, it is again back to I1. So, again when the tip moves to point 3, one is going to compare the difference in the magnitude of I3 with I1, and accordingly the tip will move. And all you need to do is you need to track with respect to the first starting point, where let us say your z is 0. No one knows the starting point, this is a very real setting. No one knows whether the starting point is the lowest point or the highest point, it does not matter, it is any random point. You simply mark it as z equal to 0, and all you are going to do is you are going to track the upward and downward movement of the tip, at the subsequent points with respect to that first starting point, which is marked as z equal to 0, and you can reconstruct the surface this way. So, STM you can go down to excellent, you can achieve excellent resolution, like you can see this the lattice plane of silicon, you can see this is a graphite surface. Limitation is STM will not work for non-conducting surface, because the fact is you need tunneling current. So, it is a fact that with only an STM you cannot really utilize this beautiful technique for reconstruction of non-conducting surfaces, and that is a huge limitation, and therefore, people started to think of how these techniques can be sort of utilized for non-conducting surfaces, and that in fact led to the discovery of the atomic force microscope. Where one needed to understand that you need a more general field which is omnipresent, and because tunneling current is something very specific, it is active a conducting tip and a conducting sample only. But if you wanted to use this type of a technique, a scanning probe technique, so we already understand why we use the term SPM. You have a probe which in case of the STM is in fact the tip, and it scans, it goes from point to gather information about that particular point. In the simplest form, it gathers the information in the constant height mode, what is the variation in the tunneling current. In the constant current mode, you have a feedback loop, and therefore, it goes up and down. So, you need a probe in order to utilize this technique, but you need some analog of tunneling current which is there and which will vary for a non-conducting surface. This is the basic philosophy of the development of an AFM. So, what can be a analog of tunneling current which is present on all surfaces, and you remember your initial discussions, something that is present between two molecules, two surfaces, which is always present irrespective of the nature of the material, polarity, etc., is van der Waals forces. So, here we go. Your probe is there, of course. So, it now measures the force instead of the tunneling current. So, STM has led to the development of SFM, the most significant member according to the image I showed, or this family tree, family history I showed, is of course the AFM. But what is interesting to note is that for a non-conducting sample, we rely on the variation of the interaction force between again a tip and the surface to gather the information about the feature height. It is interesting that an AFM also uses a tip, but this tip is, firstly this tip is much wider than an STM tip. Second interesting thing is, an AFM does not need a tip in order to generate tunneling current, but you still would like to use a tip, because you are going from one point to the other to gather the information, and if you have some probe that is very blunt, you are going to lose on your lateral resolution. Therefore, an AFM also uses a tip. But what is interesting and what becomes very exciting is how to track the variation in the force from point to point, and that is something. So, we now understand this is the genesis of van der Waals force. I will stay away from this, and because we already have discussed it in great detail. So, AFM, unlike a sharp metallic probe, also uses a tip, but that tip is mounted on the back side of a cantilever, and this cantilever is attached to a chip which actually is fixed to the instrument. This chip can be physically touched, but AFM invariably, I am sure that if you have tried to search some literature, you will see, you must have seen this picture. So, this AFM has a tip, but that tip is mounted to a cantilever. So, what is the utility of this tip and cantilever is something that we will try to understand. So, in a quick discussion, I am sure, I have already been able to give you an idea about what is an AFM. So, it is an atomic force microscope, information about the topography of a surface based on the modulation of interaction forces between two atoms or two molecules, two surfaces, let us say. So, here again it is a picture that is very similar to what we have already seen in the context of an STM, but see here there is no tunneling current, and that is what makes AFM more versatile, because you are now talking about forces. So, you can use, yes, you can also use an AFM for a conducting surface, but you can also use it for a non-conducting surface and any type of surface, because the moment you bring in a surface, and this tip I am assuming to be another surface. So, this is something I told, that between two molecules the van der Waals interaction is sort of 1 by r to the power 6, but between two surfaces it is like scales as 1 by r square. There is something you will learn in great detail, and when you bring in a tip close to a surface, there is some active van der Waals force, and you rely on that to utilize an AFM. The problem or the practical difficulty is how do you measure. The problem essentially translates to how to measure the variation in the interaction force between the tip and the surface or the sample to be examined. And why do you expect it to vary? You expect it to vary because you have taken a sample, and now according to this principle your tip is going to go from one point to the other. Because of the roughness present in the sample, what it is going to lead to is definitely the strength of the interaction forces between the tip and the sample is going to vary from point to point. Now, question comes, how do you track it, right? And of course, when the AFM was discovered, the constant, people have already understood the real strength of the constant current mode, and therefore, AFM comes with a feedback loop. So, idea is that whatever is the interaction force at the first point at which you start the rastering, you maintain that force across the sample by utilizing the feedback loop. Of course, as the tip reaches, this is a cartoon, this is not the correct picture, we will learn the correct picture soon. Of course, as the tip reaches from point 1 to let us say point 2, the interaction force here reduces because the gap has increased, and what it is going to do, it is going to trigger the feedback loop and the tip is going to come down, so that you are again back to the same force. And this way, as you complete your rastering, you again get a complete idea about the variation of the height along at every point of the sample with respect to the starting point. So, again you set this to be 0 0 and you get idea about all the other points. But still the question remains, how to track this variation in the interaction force, and that in fact is a challenge, and that is done in a very elegant way utilizing a laser source and a photo detector. So, what we will do next is we will try to understand the major components of an AFM. Of course, these are the major components. Of course, the first thing you need to do an AFM scan is a sharp tip, probe or tip, that is mandatory, because they all these instruments fall into the category of SPM. So, a probe has to be there, and for an STM it is a conducting tip that is capable of producing tunneling current. For an AFM again you need a sharp tip, but this sharp tip is made mostly of silicon or silicon nitride, is mounted on the bottom of a cantilever in a very unique geometry. So, this is the tip and it is mounted at the bottom of a cantilever. Why a cantilever? A cantilever is in fact, so if you have a cantilever like this, and if there is some force applied at the edge, the cantilever is expected to deform. So, what type of cantilever would you take? Would you take a very rigid cantilever? Well, no, because the forces you are going to sort of encounter here are van der Waals forces. So, therefore, they are of the level of piconewton, and therefore, you would like to take a very thin cantilever, so that it deforms or responds to the magnitude of van der Waals forces. That is in fact very important, right. So, if you take a very rigid, very big or a thick block of metal as the cantilever, the whole purpose is lost. You need to take a cantilever that is sort of responsive enough to exhibit some deformation to van der Waals forces. You need the tip mounted on the cantilever. So, these two, you cannot have a tip only in an AFM the way it works, because you need the cantilever. You need a photo detector with a laser source, and this is something very strange. You need a laser, but that laser does not help you in imaging. This laser is used along in conjugation with the photo detector to track the deformation of the cantilever, and that in an indirect way gives you about the variation of the interaction forces, as the interaction force between the tip and the sample surface as the tip rasters from one point to the other. You need a piezoelectric scanner. This is something that is there also in an STM. Till now I did not mention it. We have been talking right from the concept of constant current imaging, that the tip goes up, goes down, and in fact this movement is very small. It can be a few nanometer. Also, you need to understand that in order to raster from one point to the other, the tip has to physically move by very small distances, because if your gap between two adjacent points is too large, then in fact you are not going to get a good idea about the surface. So, you might want to sort of look into an 1 micron by 1 micron area laterally, and you might want to gather information about at 256 cross 256 points or 512 into 512 points. So, that means that you are splitting up this 1 micron into 512 points, where each of these points your probe will go and pick up the information. So, even the difference or the movement from, let us say, point 1 to point 2 is going to be very small. So, how do you control this? And you typically control this by a piezoelectric scanner, which has a piezoelectric material. Please feel free to check, I mean this is not feel free, please do check what is a piezoelectric material. Put it very simply, a piezoelectric material is something to which if you give a deformation, it will produce some current, or if you apply a bias to a piezoelectric material, it will change its size. So, it will deform. So, that is a piezoelectric material. So, what is done in this so called constant current mode, let us say. So, you generate the difference in the, so in very simply put, in an STM, this tip is mounted to a piezo. So, now I am giving you a slightly more detailed picture. It is mounted to a piezo. So, as the tip reaches from let us say point 1 to point 2, and you can understand that because of the proximity IT2 is going to be less than IT1. So, as it reaches here, you have a feedback loop. This is a constant current mode. So, it reaches here. In fact, we will see that this motion also we will see in the context of an AFM. I am keeping all this discussion for later discussion for an AFM. This motion is also controlled by the scanner itself, and most of the modern instruments use a single scanner. So, as it reaches here, it realizes that IT2 is less than IT1. So, this error is fed through the feedback loop, and what does this piezo do? This piezo in fact becomes long and thin. It becomes like this, so that your tip goes down all the way here. The gap between this point and this point becomes same, because therefore, the tunneling current also becomes same. Same logic is applied for an AFM also, and you need a piezoelectric scanner to achieve the rastering. So, here I will repeat, the key components are the probes or the tips. Here is a tip with the cantilever. So, this is the cantilever. You have a photo detector with a laser source. So, this is the photo detector with the laser source. You need the piezo. This is the piezo to which the cantilever is mounted, and of course, you need have a feedback control. These are the key aspects which we will discuss in somewhat detail, and we will discuss some operational aspects which are very fascinating. In fact, we will discuss what is alignment, what is approach, sample stage and rastering. The spelling is wrong, it is rastering. We will then talk about the scanning modes and data rendering, and this is where you actually generate the so called image of the surface, because till now whatever we have discussed, we are only seeing, we are not getting a picture, we are only getting an x, y versus z data. So, how you generate the image we will discuss. Running out of time, so we will stop here and start from the different components. In fact, we will start with the key components and talk about next lecture. Thank you very much.